second lecture on chapter 15, and we're going to be covering oxidation reduction reactions in metabolism. So you'll see that I still have that learning objective for defining and explaining Gibbs free energy because we're going to talk about it with biochemical reactions. And then I'm going to want you to be able to describe the role of high energy carriers in facilitating reactions. Okay, so oxidation reduction reactions are going to require the transfer of electrons from a donor to an acceptor. In oxidation, you're going to have a loss of electrons, and the thing that loses the electrons is called the reducing agent. In reduction, you have a gain of electrons, and the substance that gains it is called an oxidizing agent. And here's a simple mnemonic that you guys already told me about. Oxidation is loss, reduction is gain. Oil rig. We're going to look at the example your book uses to see how, in this reaction, electrons are transferred from zinc to copper. So we have one half reaction where there's a reduction, where the electrons are donated to copper, and the second half reaction, zinc is the one that's donating the electrons. So in this case, zinc is the reducing agent and copper is the oxidizing agent. So we talked about catabolism and anabolism in the first part of chapter 15, and now I just really want to point out here that catabolism, overall the process is one of oxidation, and anabolism, overall the process is one of reduction. The book gives you another example of an oxidation half reaction showing the conversion of ethanol to acetaldehyde, and they use Lewis structures here to show how electrons are transferred. And the point of all of this is to reference coenzymes. So the first coenzyme they're talking about is nicotinamide adenine dinucleotide. And this acts as a biological oxidizing agent. And basically what happens is two electrons are reducing NAD, nicotinamide adenine dinucleotide, to NADH. Here's the structure of NAD, and they show you in the purple box the oxidized form, and then that two electrons and a hydrogen ion, which together are called a hydride ion, are donated to produce the reduced form of the coenzyme. Another important coenzyme to know about is flavin adenine dinucleotide, and in this case you have two protons along with two electrons that are accepted. So FAD is considered the oxidizing agent, and it is reduced to make FADH2. And this image here just gives you the overall structure of FAD. NAD plus and FADH are super important because they provide the energy needed for anabolic pathways. Another way that energy can be provided for anabolic pathways is via high energy bonds. And breaking of these high energy bonds provides a convenient amount of energy for anabolic pathways. ATP is a commonly used molecule that provides energy for endergonic reactions. So basically, phosphorylation of ADP into ATP requires energy, and it creates these phosphoric and hydride linkages. But hydrolysis of ATP breaks those bonds, and it releases energy, and thus it can provide energy for other reactions. ATP is a high energy carrier. So in order for ADP to be phosphorylated into ATP, you need energy from oxidation of nutrients. And then hydrolysis of ATP to ADP releases that energy so that anabolic processes have energy to proceed. Coenzymes often have to be activated. And the example they give you here is of coenzyme A. And coenzyme A is one we'll see later when we look at the Krebs cycle. But basically what you see is you have an activation step where a substance is bound to the coenzyme, and then you have the exergonic step where that coenzyme releases the substance with a release of energy. Here is the structure of coenzyme A, and pay special attention to that functional sulfhydryl group at the end. And what you see here is that the sulfhydryl group is lost, and there's a thioester linkage to an acetyl group. And that forms acetyl-CoA that donates 2 carbons to the Krebs cycle. And then when those carbons are lost later on, that is an exergonic reaction. So you have a high release of energy, or a very negative delta G in that process, which provides the energy to push forward the Krebs cycle. So what you're going to see in catabolic pathways is that NAD is reduced to NADH and ADP is phosphorylated to ATP. And then this energy that's put into those molecules in catabolism is used to drive reactions in anabolism. So you see that ATP is hydrolyzed to ADP, NADH is oxidized to NAD+, and then NADPH, which I haven't talked about. And then finally, you see a coupling of reactions in the citric acid cycle. So this is a little bit more complicated, but ultimately you have catabolic reactions that are coupled to anabolic reactions, providing the energy needed to drive those anabolic reactions. So your takeaway here is that coenzymes and other high energy carriers like ATP couple energy harness from catabolic reactions to drive anabolic reactions. That's the end of chapter 15. Again, I want to remind you that you have homework assignments that we're going to be working on today. Questions 10, 11, 12, and 14.